Alright, welcome to the second video of Grasshopper Week 6. So this file is the Surface Connect example. And here you'll see I have a couple curves in here. One is called a section curve, input curve 1, and input curve 2. Right? So this is actually a surface we'll build up by using the sweep2 command in Grasshopper. So sweep 2. And it's asking me for first rail, second rail, which are these two, and a section curve, which is this one. Same height, we don't need to change that. Okay, so very simply, let's go to geometry, parameters, geometry, pop in a couple curves, right? Align them, distribute them. Rail 1, rail 2, and section. And let's link these in. Set one curve. That one, set one curve, this one, and then a section curve, this one. So you'll see we get a lofted surface. Alright, and don't worry about the Jackie, that's just, you know, Grasshopper kind of trying to draw it graphically faster to kind of not bog down the system. Okay, so we're going to kind of look at similar ideas in the context of a surface like this. A surface you've created. This could have been a Rhino model surface. It would probably work the same. But in this case, this is a swept surface, but subdividing a surface. And the two main different methods, I guess I would say, of doing this. All right. So if you go to the Surface tab, and under Utilities, there is a Divide surface. Generate a grid of UV points on a surface. Okay. So it's asking me for surface divide, which is this, and then automatically some UV points pop in, U and V, right? 10 by 10. It's set to 10 by 10. So let's make a number slider, goes from 0 to 20, integer. Oops, wrong one. That, and let's do more on this direction. So let's say 20 to 10, something like this. Okay, so U count versus V count. All right, so now we have a divide surface. Let's take a look at this really quick. And you have the what? These are division points, normal vectors at division points. We're pointing sort of outwards, perpendicular to the surface. And UV parameters, which are basically coordinates on the surface. Okay. If you're curious, we can look at the normal vectors really quick. It's under display, vector, vector display. And so let's say anchor points for preview vector and vector to preview. Anchor points are actually these, the division points, and the preview vectors are these, the normal vectors. So it'll basically kind of show you these little arrows that are the vectors. Right? If they're too short, too small for you to see, you can multiply a vector by any sort of amount. Let's see, 5.00, number slider like that, and push that into the vector, so you get a much bigger vector display. Maybe actually 5 isn't even enough. Change that to 20. Okay. That gives you a very good visualization of the vector, normal vector direction. And these are basically sort of lines that are perpendicular to the surface at that point. Right? That's what normal vector means. And that's actually a concept we'll be using later on in the last video of this week as well. Right? So that aside, this is just something to kind of help you visualize. Okay. All right, so what we want to do here is actually just like kind of look at these for now. Let's do a points list again, a point list, and look at numbering scheme for this guy. Set number to, I don't know, it might be have to bigger, like 10. Oh, too big. Set number, let's say 4. Okay. So you'll notice, similar to the previous file where we were looking at this, the square grid, this thing does the numbering thing the same way. The surface divide numbers it the same way you do the square grid, right? So it does it in rows and columns. And you know, for something like this, this is actually, depending on what we're trying to do, it can be good, it can be bad, right? And so once we see the other version, you'll understand a lot better why. Now, for the purposes of this example for now, I'm not going to do too much to it, because if I take this surface and let's say I graphed it, I'll just get zeros everywhere and I can't do anything. If I flatten it, I'll just get a zigzag, you know, across the surface. And if I try to kind of draw polylines that go between them, it's kind of useless as well, right? So what we can do with this really right now at this point is actually, let's try to get an offset surface, right? Similar to the way, you know, you kind of got a grid from paneling tools, right? This is a sort of paneling point grid, or the idea of a paneling point grid. Okay, so let's find the offset, and first you'll see there's actually a couple offsets. Offset curve, which we don't want, we want an offset surface, right? So the offset surface, and give it the sweep 2 surface, the original one, and a offset distance, and a retrim offset true or not. Okay, so offset distance, let's go from 0 to 10. All right, push that in. Okay, so now you'll see that this is basically the offset surface, and you can control the distance. Okay, let's just duplicate this, SDivide, and push the offset surface in there, and you basically get a duplicate set of points, right? From here, what we can do is actually reconstruct the relationship between these points. So, for example, if you push a line, take those points A and B, and then you get this sort of thick connection between them. Right? And it's really easy at this point to say, well, okay, we can just, let's say, pipe these curves. If that's too big, let's do 0 to 1.0. Let's put 0.3, for example, so it's a little skinnier. Okay. Right. So this could be a sort of more thickened facade system. All right. So if we look at the points numbering scheme of this, you'll realize very quickly that because it kind of works on the scale of the overall surface, right, that your options really in terms of, let's say, if I wanted to make a truss framework for this, are a little bit limited, right? The only thing you can do is, let's say, for example, try to draw polylines that follow this, right? Follow this sort of numbering scheme. I'm just going to do one for, let's say, the inner surface. So to kind of do that, you would put in, let's say, a polyline component, and that automatically draws, in this case, horizontal lines, right, that go left, right, 0, 1, 2, 3, blah, blah, blah. Okay. As we learned earlier, to get the verticals, you would have to do what? A flip matrix, right? And then do the polyline command again, except this time using the flipped matrix. So now you can get this sort of crossing rectangles, right, of the framework. And that would look like this. Same thing. You can pipe it. Push that in. Right, so these are the horizontals. I'm going to hold down Shift and push these in as well together. And I'll run for a couple seconds. And they'll pop in. Alright, so then I can kind of go to the back side and say, okay, these are the rectangular frames, right? And if I wanted to, I could kind of change the radius or make these beefier. 0.6, for example. And because this is, you know, essentially, I don't know, 300, 400 polylines, it's going to take longer for it to update. Because I think there are, what, 32 of, you know, really short segments each, right? So, alright, so you'll kind of notice, at least in this case, that inherent to this sort of numbering scheme, where it's going from 0, 1, 2, 3 like this, you can make a square grid, you know, fairly easily. This is basically a sort of box truss, like we have right now. You can do it for the outside, but if you're kind of trying to do anything, let's say like having diagonals between them, things just get, you know, really tricky, right? Because a lot of these are duplicates. You know, if I'm trying to draw a diagonal line from here to here, I'm connecting the 0 to the 1, the 1 to the 2, the 2 to the 3, the, you know, even kind of using, let's say, shifting lists will only get you so far, because, you know, your list shift all the way over there and that sort of thing, right? While shifting lists, you know, a la the earlier please example, will kind of work again, you know, in one tier. Then you would have to do, you know, 9 or 10 or however many of these for each and every sort of tier, right? That's a pain in the behind to actually work with. Flattening it or grafting it really doesn't buy me anything, because obviously grafting it only turns all these into 0, right? And then you have even tougher time kind of differentiating between the points. Flattening it makes this into a long list of different numbers, where technically you would be able to work with it to a certain degree. So let's look at this. For example, then you can say, well, you kind of would have to do the math and say, well, I want to draw, let's say, 0 to 22, 1 to 21, 21 to 13. And these are like offset by the same number, right? They're basically plus 23 between them. So you could kind of do some fancy math and be able to address the points individually, right? But still, you know, real pain in the behind. Okay? So this is one of the, in some ways, you know, one of the inherent disadvantages of this. If you want to actually get fancy, you can actually connect in these directions as well, right? So you could actually kind of try to address the 0 point on here and address the 22 point on the outside layer. If we kind of did the same thing on the outside, actually draw a three-dimensional diagonal, so to speak, instead of a flat diagonal. And it becomes a 3D truss, right? So, you know, in the sort of context of this little cell, then, you know, these are some of the possibilities. But as you can see, this method is a little bit harder to deal with. So as you can see, selecting, you know, a specific point on this is, you know, a pain in the behind, and being able to address these across things systematically is very, very, very difficult to deal with. All right. So while it's not impossible, to kind of work with this logic where the points are ordered like this. Obviously the worst thing you can do, or the sort of destructive thing you can do, is to flatten the list and then pick the numbers individually like I just had. One of the questions becomes, can I actually address one of these points individually without destroying the data structure? And there is a way called the branch, the tree branch. Okay. Tree branch asks for data tree, which is the points, and a tree branch path. And by path, it means one of these, 0, 0, 0, 0. Which path are you looking for? And then that will select that branch. And then we can eventually use the list item to select that corresponding item on that branch. Now to kind of get this tree branch, there are two ways. One of which, and let me make this first. How many are there? 0 to 20. Okay. So 0 to 20 goes into the item here. Whoops. Undo. Goes into the item here. So this, let's say I'm looking at that bottom row. The first one is 0, 0, 0, 0, right? So I can actually just do that by text using curly brackets. 0, semicolon 0, semicolon 0, semicolon 0, enter. All right, so this is basically that. Pull that in. So this means I'm selecting that first branch, which is this bottom branch, and I'm selecting the first item in the list. So you'll see the green dot here lighting up. Let me make a sphere, just so you can see it better. Radius 4. Right? So that's what I'm selecting. So if I move it, that's where it goes. All right? And let me close this. Hide some of this stuff. So I'm selecting this. This allows me to select horizontally in this sort of data matrix, and I can change this to select vertically. But still, having to type this in one by one is a pain in the behind as well. So actually, let's try using our good old friend, the param viewer, pulling the points into here. Okay. Same thing. Let's use this item. List item, and you'll see the list item actually gives me the path, right? So the first path is 0, 0, 0. The second path is 0, 0, 1, 0, 0, 2, 3, 4, 5, and blah blah. This only goes up to 11, so you would change the boundaries of this from 0 to 11. Make sense? Or actually 0 to 10. Okay, so that's the last one. And this goes to 0 to 21. All right? So with that, then we're actually able to replace this sort of text input, stupid text input, and put that into that for the branch. And I actually can move vertically now. All right? So this is a way you can actually address single points within a data matrix that looks like that, but that's sort of in rows and columns like this. All right? Okay. So let's leave this at that. This is just kind of shows you some of the limitations of this sort of method. But let's actually keep on using this. And what I'm going to do is like select everything, space bar, and then hide it, disable preview for all that. Okay? And we're going to move this down to do the next part. So that was one way of subdividing a surface. One of the other ways that you've been using actually is the Lunchbox, right? Now the Lunchbox component in this regard is actually really nice. And even if I try to replicate the same thing by using here the quad panels, okay, of the Lunchbox component, and we'll just connect the surface down here. All right. We'll even duplicate the same UV count that we had, so it's similar. I'm going to hide the original sweep too. And you'll see this actually automatically, this gives us, in this case, you know, rectangular quads. And you can kind of see it in the shading as well. Alright, now the output of this is panels. If you put in a panel, look at it, okay, these are just surfaces, more or less. Not organized in any particular order. Right? There's 200 of them all in one long list, essentially. Right? So nothing particularly special about that. But one of the key things, right, most commonly used components we use is the decompose or deconstruct BREP. Right? I think it's under surface analysis deconstruct BREP. Okay, let's pull that in, and you can hide the quad panels, Control Q. So this gives me faces, right? And you just kind of look at this untrimmed surfaces, more or less the same what we had there, right? Although it's all grafted, ordered differently, right? Okay. Edges. Ooh, this is nice, right? Because it's actually taking the cells, each face, and then pulling out the individual edges. And it's organizing it in a way that makes sense, right? Because this is essentially that first 4 sides. This is the second 4 sides, etc. So it's actually arranging them into the 4 sides. Vertices as well. It's arranging them into, let me pull it out, 0, 1, 2, 3. So it's arranging them into the 4 vertices, 1, 0, 1, 2, 3, according to panel instead of in rows and columns, right? So that actually makes addressing specific points or edges or sides on this thing a lot easier, a lot easier, all right? So immediately, you know, what we can do, let's pull out our good old friend, the points display. Copy, paste. Look at the vectors, the vertices. Whoops. Enable and turn on the preview. Okay, if you zoom in a little bit, there's a little bit of overlap, right? But essentially what's happening is 0, 1, 2, and 3. And then 0, 1, 2, 3, 0, 1, 2, 3. It's probably easier to read, let's say on the top, because then you can tell that's 0, 1, 2, and 3. The colors show you which ones are together, right? So this sort of light lavender is 1 that's together. This blue, 0, 1, 2, 3, those are the ones that are in the same sort of bag, same list. Okay, that's how you kind of read this, which is fantastic. Because of that, this data structure, what we can do, let's say, remember we were kind of trying to draw diagonal trusses, right? Easily by using this list item. Okay, you can grab the vertices, and it goes 0, 1, 2, 3, so we can change the bounds of this from 0 to, let's say, 3. Okay. All right, and duplicate it twice. So let's say we're drawing here to here, that's 0, 1, 2. So we're drawing from 0 to 2. Okay, so we want to check 0 and then 2. And then just do, let's say, a normal line between 2 points. Push that in, and you see diagonals. Okay? And you'll see that I can, for example, I can flip this around. Let me hide the points now. I can flip this around. If it's 3, then this would actually be the horizontal, and 1, that would be the other diagonal. Right? So that's great, because then, I can just, if I wanted a cross, I can just duplicate this assembly again, 1, 3, and 0, 2. And so I have a cross truss. And remember that, let's say in the early example, when you offset it, you can actually more even easily basically connect between surfaces as well, right? And actually do a 3-dimensional one if you so desired, by having the surface offset, doing the same thing, and then connecting the let's say in this case the 0 from one side to the 3 on the other surface, right? And you would get a 3-dimensional truss. Okay, so that's really fantastic, and you'll kind of like see how components that, let's say in terms of surface subdivision, components that organize the data this way can be a lot easier to deal with in specific cases. So to get the same sort of structure that we had, or similar structure to that we had earlier, then you would basically pipe, grab these together, right? Let's give it a radius that makes sense first. Let's go up here, delete this, 0.4. Radius, and that, and that. Holding down Shift to add them together, right? So I have my diagonal pipes. And I want basically all the edges, right? So these are the edges of the B-reps. There's going to be a little overlap here because your edges actually double up in this case, and we'll get into how to deal with that later. But do that, and let's say make these beefier. Then you get essentially a diagonal truss. This, in many ways, if you look at the Lunchbox plugin, is basically some of these options, right? It's like that. The tri-C more or less is what we did, and you can work with that as well. The data structure would be different in this case, because instead of being in quads, these would be in triangles, right? Because that's the subdivision. So you would have vertices of 0, 1, and 2. And that might be good, may be bad, depending on what you're trying to do, right? Because at least in this case, if you get panels like this, you wouldn't actually be able to kind of differentiate between, let's say, the orthogonal ones and the diagonal ones, right? So, there's trade-offs between, using these different options and what essentially in the end that you're trying to do, right? So even though on the face of it they might look similar, or they might yield similar results, because of the way the data is structured, it actually will be harder to be able to do this with the tri-C panel version. Okay? Alright, that's it for this video.